Howdy, this is Jim Rutt. This is a continuation of my podcast with Lee Smolin. So why don't we start to move on to what happened after Bohm and the development of some of the scientific theories in the realist branch?
Well, so the key issue is, if you're a realist, what is the mystery about? It's not about uncertainty, because the pilot wave theory explains what's going to happen and resolve the problem about uncertainty. It's not about complementarity. What is the real mystery about? And Einstein, again, in his last paper about quantum mechanics in 1935, kind of almost accidentally finds the key thing. The key thing is what we call now entanglement. Entanglement says that if two quantum particles interact and then separate, and they may go a long way from each other, meters or light years, then they share properties in ways that can't be attributed separately to either one of them having a property. And this is entirely unlike the rest of science, the rest of physics. The idea that two particles distantly separated but having once interacted share properties which cannot be attributed to either one separately, or any combination of properties that either one separately may have. And this concept of entanglement, we understand now, is what makes quantum mechanics radically different from the rest of physics. Indeed, all the exciting stuff going on now, such as the attempts to build quantum computers, which would be able to break codes and do things that no normal computer could do in a finite amount of time, all rely on this property of entanglement. And entanglement is now something that the experimentalists study and control, indeed think of as almost as an engineering resource. So this property of entanglement should sound strange to somebody, because it means that there's a way in which the two particles are linked, even if they're very far apart from each other. And that violates the principle that physicists have held to be sacred, which is locality, which is that influences and forces travel through space from one point to another and don't act directly, jumping over big regions of space.
Wasn't Einstein skeptical of entanglement? I think I recalled he had a paper. Was it the EPR paper?
This is the paper I'm referring to in 1935.
Yeah, where he called it spooky action at a distance, and was really put the paper out to say there must be something wrong with quantum mechanics if this is what it implies. And yet, as I understand it, and you could correct me on this if I'm off, that modern experimental physics has shown that the EPR effect is actually what happens.
Yes. Now, what happened is that Einstein and his young collaborators, Podolsky and Rosen, Boris Podolsky and Nathan Rosen, fashioned an argument which assumed that there were only local influences, and came to a conclusion that quantum mechanics had to be incomplete, to give an incomplete description of reality. And their assumption that there were only local influences was wrong, so their conclusion could not be held. But nonetheless, the paper was a breakthrough paper, because it led to the recognition of this property of entanglement, which was then found and measured by experimentalists to be real. Now, the next person in the story is an Irish physicist called John Bell, who was a particle physicist. And he came along in the 1960s, and he fashioned an elementary, very easy to formulate and check and prove theorem that if locality were true in cases like this where two particles interacted and then separated, then there was a certain constraint on measured values of certain correlations, and there's no reason to explain it here to your viewers. He could derive a certain constraint on measured values in some experiment. And the assumption was that when the particles were very far apart, that what one chooses to measure of one of them doesn't affect what's true about the other one. And if you're a realist and you believe in locality, how could it be that whether I choose to measure the position or the momentum or something else of a particle that's come over here to my laboratory shouldn't affect, it's obvious that that shouldn't affect what's true about a particle that maybe now is somewhere around Mars or Jupiter. And just making this assumption, which we call now Bell locality, Bell proved this inequality had to be true about the measured values of certain observables. And then he could do the calculation in quantum mechanics and show that the values predicted by quantum mechanics contradicted the inequality. So that meant that that property was false in quantum mechanics. But the dramatic thing, which was demonstrated a decade later, starting in the 1970s, is that people could do the experiment and find that the inequality was violated in the experiment. So without any reference to quantum mechanics, we have tested this assumption about locality, and it's false, and not just by a little bit, it's dramatically false.
I think this is big. This is a big story for our listeners, is that realism can include non-locality.
No, Jim, let me put it to you stronger. Realism or non-realism, non-locality is part of nature. This experiment doesn't assume any philosophy of nature. It just describes certain correlations between measurements you might make on a pair of particles and makes that one assumption. And believe me, people have combed this thing. It's a very short paper. There's not much to it. The other assumptions that go into the calculation are trivial things like probabilities or numbers between 0 and 1, which you can try to disbelieve if you want to get out of it. But I think everybody would agree that if probability means anything, the probability of something to happen is between 0 and 1. So people have looked for loopholes, people have looked for mistakes, and it's pretty remarkably solid at this point.
Those of us who looked into this as educated laymen have seen the claims that despite the fact that there appears to be an instantaneous effect faster than the speed of light between entangled particles that are far apart, there is no way to actually send information faster than the speed of light. Is that something you can talk about?
Yes. This goes back to the randomness you asked me about at the beginning of the show. Because if we look at any one detector for one particle, the outcomes are random. It's only when you look at the correlations of the statistics that you get by averaging over many instances of measurements on these pairs of particles that you see the observable and construct it that John Bell was pointing to and see that it violates the assumption of locality. So because quantum mechanics and quantum physics, as far as we can tell, is statistical, you can send information faster than light. Now, there are twists to this because let's go back to the pilot wave theory. In the pilot wave theory, how does it agree with the statistics of quantum mechanics? You have to make an assumption, which is that if you make an ensemble of trials, if you do an experiment over and over again, the wave is always the same wave, but you start the particle at different places in different runs. And what do you assume about how you choose the starting points for the particles in the different runs? You assume that the particles are distributed in the different runs by a probability that's related to the square of the wave. And that's called Born's rule. That was one of the fundamental principles of quantum mechanics, and it has to apply to the pilot wave theory as well. Well, there are 2 points of view to take to this, the traditional one, and one which is argued for by a contemporary physicist called Anthony Valentini. Most people, including Bohm, and for that matter, de Broglie, to the extent he understood this question, would have said that's one of the assumptions, it's one of the inputs of the theory, that you just have to distribute the particles according to that probability distribution related to the wave. What you can show is that once you've done that, initially it stays that way, so that as the wave evolves in time and changes, and the particles move around guided by the waves, the probability distribution always stays related to the square of the wave. And that's an important result that tells you that the results of any experiment are going to agree in pilot wave theory and in ordinary quantum mechanics. But Anthony Valentini said, supposing that you start off with a probability distribution different than that related to the square of the wave, you just put the particles in any old way you want, different from that assumption, what happens then? And he called that being out of equilibrium or out of quantum equilibrium. And Anthony Valentini was able to prove two remarkable results about that. One of them is that the system will evolve in time so that pretty quickly it gets back to the Born rule. So that even if you start off with a probability distribution for the initial particles, different than the square of the wave, everything somehow conspires so that pretty soon the distribution is the same one, like the square of the wave. That's the first remarkable result. The second one is that during the period, however, when you haven't reached the square of the wave as the probability distribution, you can send information faster than light.
Have there been a demonstration of that?
People have tried, not that hard, but people have looked for that and so far not found it. It's given rise to any number of science fiction books, some of them good, some of them, well, I'm not really standing in judgment of science fiction, but science fiction books and ideas of varying quality in which people, aliens or the military or little high school kids or not so little high school kids, use this to send information faster than light. But it's standing as an open hypothesis.
And is there a well-defined set of experimental protocols that could demonstrate this if we had the right apparatus?
Yes.
That's very interesting. I'll have to keep my eye on that.